Okay, now suppose we want to express our vectors in our composite spaces. Okay, vectors in composite spaces. All right, so we saw in the last module that if I have a vector like this, if I have a vector like this, u, which is a0 plus b1, I can write this vector. These two actually denote the same vector. Writing this column vector ab and writing this vector in this expanded form. All right, they denote the same thing. All right, so in the last example we saw that we had a vector in the space A and a vector in the space B. Okay, and after expanding them out, we had the vector well, this was, well, I will just go back, and this was the form of the vectors. All right, a0 plus b1, c0 plus d1, and we expanded out and we got this form. Okay, so if we want to write this vector in a column matrix form, what would be the column matrix? You see, we needed two numbers in this column vector because our space A was two-dimensional. We needed two numbers in this column vector because our space B was two-dimensional. But our space AB, our composite space AB, is four-dimensional. So we need a four-dimensional column vector. What would be the components of this four-dimensional column vector? Well, the components would be AC, AD, BC, and BD. All right. Okay. So if we had a U that was a column vector AB, and if we had V that was a column vector CD, then the composite vector UV would be the column vector AC, AD, and BC, BD. All right. So to denote vectors in this composite space, we formed a product previously. All right, this was a type of product. All right, to find these column vectors, we will introduce this new type of product between two vectors. All right, we will call this a tensor product. Okay, so what is the definition of a tensor product? Well, the definition of a tensor product is, suppose I have a vector AB and I want to form a tensor product. We denote tensor product in this fashion. We give a circle and we give a cross inside the circle. This denotes tensor product. Tensor product. All right, so we want to form the tensor product of AB with the tensor product of CD. The rule to do that is we will do this. The result will be a four-dimensional vector. We will write the first element of the first vector times the second vector as a whole, and the second element of the first vector and the second vector again. Alright, and if we multiply this out, we get A times C, AC, A times D, AD, B times C, BC, and B times D, BD, which was our original state vector. Alright, so this is the definition of our tensor product. This is the definition of a tensor product. If we have one vector with components A and B, the first vector of the first space with components A and B, and the second vector of the second space with components C and D, then the components of the vector in the product space, in the combined space A and B in the product space, will be the tensor product of these two vectors. And the definition of the tensor product is you will take the first element of the first vector and then write the second vector whole, and you will take the second element of the first vector and write the second vector as a whole. Okay, so I can actually show you this tensor product doesn't have to be for qubits only. You can generalize this to any number of dimensions. In fact, these two dimensions don't need to be equal at all. Okay, suppose I want to do something like this. Okay, I have this is an example. I have a vector A1, A2, A3, and I want to form the tensor product with a vector B1, B2. Okay, so what will be the tensor product? Well, the tensor product will be, write the first element A1, then write the second vector as whole B1, B2, then write the second element A2, then again write the second vector and write the third element A3 and write the second vector. Alright, and if we multiply this out, this will be A1 B1, A1 B2, A2 B1, A2 B2, and A3 B1, A3 B2. Alright, well, this is the tensor product. Okay, so using tensor product we can find the components of the vector in a composite space if we know the components of the vector of the individual spaces. Alright, okay. Since we can form the vectors of a composite space using the tensor product of the vectors of individual spaces, well, for the at least for the examples that we saw, since if we know the individual vectors of the individual spaces, we can form the composite vector using the tensor product. A composite space is also called a tensor product space. Alright, so a composite space is actually called a tensor product space. Alright, actually the name composite space is not used too much. All scientists and mathematicians use the name tensor product space, so we will be using that name from now.